So trees, we talked a lot about trees and we will see some examples, but what are the issues that we may face dealing with trees? There are three major issues. One is instability, the other one is lack of smoothness, and the last one is difficulty in capturing additive structures. So what do we mean by each of them? Okay. So why do we call why are they unstable? Because they tend to overfit, and when they tend to overfit, um, the model becomes very sensitive to the data. You may say, then what about cross validation? How can we use cross validation to avoid overfitting? Yes, we can use cross validation to avoid overfitting, but since we're partitioning the feature space into these regions, which are built out of horizontal and vertical hyperplanes, then a single observation may um, change the location of these um, separations. Lack of smoothness, because the regions are blocks. They are just these blocks that are next to each other. And difficulty in capturing additive structure. Let's look at this example. Imagine this is a two-dimensional, we have two features, x1 and x2, and we would like to separate the space using, essentially imagine that the features are such that here we have yellow, here we have green, and we want to capture this separation. Obviously, a single line is sufficient, and logistic regression would do a great job for data that has this structure, but a tree would try to cover these two different regions using many regions, but regions that are meant to be horizontal and vertical rectangles. So a tree would cover this, would block this, and so this would be yellow, this would be green, so this part would be an error, this would be an error, this would be an error, this would be an error, and this would be an error, and this also would be an error. So we would have a tree with 1, 2, 3, 4, 5, 6 nodes, 6 leaves, 6 regions, and yet it is not able to capture this linear boundary perfectly, which logistic regression is able to capture. Now, on the other hand, if the structure of the data does not allow itself to be separated by a plane, then and here's an example. So we have this strip of green surrounding this square of yellow. There's no logistic regression. There's no linear boundary that we can find that would do a great job in separating these two regions according to their colors because of the way the regions are separated. But a tree with 1, 2, 3 nodes, 3 regions, 3 leaves would be able to perfectly capture this structure in the data. So depending on the data, a tree might work well or might work terribly. Okay. So in order to address these problems, um, bagging, random forest, and boosting have been proposed three different approaches of combining trees to construct more powerful predictions. So trees are the building blocks, but instead of having one, we use many of them. Bagging. What bagging does is essentially it is fitting B trees to B different data sets. These B different data sets are created from the original data set. So we have the original data set, and then we create a new data set by sampling with replacement. So we sample with replacement the original data set, and then we create a new fake data set. That new fake data set, because we are doing resampling with replacement, will have repetitions, and each sample, each resampled data will be different slightly, with a lot of overlap though, and each of these we call it a bootstrapped data. Bootstrapping means resampling with replacement. Okay, so we have B bootstrap data sets, we have B data sets that are just resampling the original data set, and to each of these bootstrap data sets we fit a tree. These trees will be slightly different. The idea is that these trees will be independent because we fit them to be different trees, and by averaging them we are able to reduce the variability. By averaging we are able to reduce the variability. So we reduce the variance. A tree is very unbiased because it's flexible. So but the problem a tree has is the high variance. So therefore we what we do is we um, aim to average B independent trees to reduce the variance. And how do we get B independent trees? By fitting B trees to B independent data sets. Well, we don't have B independent data sets, we have one data set, but we can resample that data set B times, excuse me, we can perform resampling to it B times to create B sort of independent data sets. So, and then what we do is when we want to do a prediction, we pass the feature through the B trees, and each of them will come up with the classification, and then we assign the majority class to the predicted label. There's a smart way of calculating the cross-validity. Essentially, there is a smart way to estimate the test error for bagging. And the idea is that since these trees are fit using different data sets that have 2/3 overlap on average, 1/3 of the rest of the data is not used, so we can use that to test because the 1/3 of the data was not used to fit the tree. And then we can use that to do efficient cross-validation because we can estimate the test error using the out-of-the-bag error. So bagging improves prediction accuracy, but it loses interpretability because there are many trees, and once you have many trees, these trees are different, and then well, each of them is interpretable, but you have B trees, so it will lose interpretability because each of them will tell a slightly different story. But if you average the responses, then we have a reduced variance and improves prediction. Okay. So then if we, in order to retain some interpretability, there have been some heuristic ways been designed to quantify the importance of each predictor. And the way it's done is that internally under the hood, splits over a predictor are removed, and then the amount of error that is increased by this removal of these splits corresponding to that predictor is measured, and then it's averaged over the B trees, and that gives you a way to quantify the importance, even though it is not very reasonable. But here's an example. You get some number between 0 and 100, and then you can rank them, and some people use it, some people don't, and in my opinion, it is it is useful. Such a graph is useful to say that, yeah, the thalamus in this for the hard data is an important factor, much more than, I don't know, FBS, for example. So that sort of conclusions or we can make. But when it comes to, for example, even calcium and chest pain, yes, calcium is higher, but I don't really know if this difference is something meaningful. And we don't even know exactly what we mean by importance here with positive, negative, in a complicated, non-linear way. That's the difficulty we have with bagging. And whenever we average many models, which bagging is in a way averaging different trees. So bagging has a problem. Bagging uses bootstrapped samples. These bootstrap samples have two-thirds overlap, 66% overlap. Therefore, these trees are not as independent as we wish them to be. They are not as independent because the data that was used to grow these trees has a significant amount of overlap. So what can we do? One smart approach, this is a new idea so far introduced in this class, this is a new idea, and adding randomization. We add noise into our process. We add noise into the process of growing the trees so that these trees might be slightly worse trees, but at least they will be more independent. And then when they're more independent, when we average them, then the variance will reduce. Because if you average variables that have dependence, then the variance may not reduce as much as you expect. So independence is important. And how does random forest perform this? How does it decorrelate trees? What it does is when it grows a tree, whenever it looks for a specific, for the best split, instead of considering all the features as candidates for the new split, it randomly selects a smaller subset of all the features, typically, well, it's called M, and it's a free parameter, but typically we set it as square root of P. So a much smaller subset is randomly selected, and then all the best splits among those features are considered. So when we grow the tree, we don't have the option of considering at each stage all the features for the splits, but eventually we will go over all of them because this randomness will cover them. But in the growing process, we introduced some randomness. So each tree has some unique randomness, which makes them sort of more independent than what bagging does. Okay, so the take-home message of this graph is that the number of trees, which corresponds to the number of bootstrap data set, as we increase it, yes, it typically reduces the error because we are just reducing the variability. But after some point, which apparently happens around 100, I think for different data sets it's different, but it's a good place to start. It leads a pretty constant error rate life, and we can also see that random forest is performing slightly better than bagging because of this. You see this gap and you see this gap. Random forest is performing better because it deals with the high correlation that these trees have. So in bagging, their variance does not reduce as much as we expected because these trees are very similar to each other. And apparently, if random forest is performed with m equal to p, then we are back to bagging. If at each stage of growing the tree you allow all the features to be considered, you're doing bagging. If you limit that, you're doing random forest. So in this example, again, we see that increasing the number of trees initially reduces the error rate, but then it kind of saturates. So there is no point, not saturates, but it plateaus. There is no point in cross-validating over the number of trees. We see that in terms of the how many features we keep in when we grow the tree. If it's m equal to p, is essentially bagging. If you do m equal p over 2, it doesn't change much. But if you reduce it significantly, so you limit the number of features that are considered for splits as we grow the tree to square root of p, then you see that classification error rate drops quite a bit. Okay, so in this R example, we'll go over some um, or the college data set, and we use lasso, ridge, elastic net, and logistic regression together with random forest and trees. So my data here is you have these colleges. The target is to predict whether it's private or not. And then we have these features: applications, accept, enroll, top 10%, top 20%, etc. Here we read the number of observations, P number of features, X is our design matrix or feature matrix, Y is our response, and then we turn it into numerical, right? So Y now is not anymore categorical here. Y is a numerical 0, 1. So alpha elastic net, well, let's just ignore that. So we give X, we give Y, the family is logistic, alpha is lasso, we use an intercept, we do tenfold cross validation, and the measured that we use for cross-validation is misclassification error. We run this, right? Then we use the lambda that minimizes the cross-validation error and fit the model again. We get the lasso object. Then we use the predict function, give it the lasso object, fit it to this data, give it some new data which is essentially the same data it was used to fit, and we say give us the predicted probabilities. Then we create here the predicted labels by thresholding that probability at 0.5. Then we calculate the false positives, true positives, total positives, total negatives, type 1 error, type 2 error, and then we print it. So the reason I'm going over this is because we've done it before. Okay, so this is nothing new, we just put it all together here. Then I create a bar plot of the coefficients that the estimated coefficients of lasso logistic regression, right? That gives us a sense of what is important, what is not important. Then I repeat the same thing for elastic net. For elastic net, the code is exactly the same, except that alpha is now 0.5, right? It's 0.5. Everything is the same, and then we look at the bar plot of elastic net, and then we set alpha as 0, alpha 0 here, and then we just do the same thing for ridge. Now here is a difference, just a small difference. You see, here we use the lambda min given by the lasso object. This lambda min is the lambda that minimizes the cross-validation error. Here we're doing it different way, it's just a little more complicated, but it just gives the same result. We go over all the lambdas and we use the lambda for which the cross-validation error is the smallest. The same thing for ridge, and then we have the bar plots. So let's just do this. So I googled the error, and that's the answer. Expects a matrix. Okay, so I just have to do that as matrix. So here, when I make x, I just do x. I hope this resolves the problem. Oh. Okay, resolved. Okay, so type 1 error is 0.13, type 2 error is 0.03. And these are the coefficients we have, right? Yeah. We do elastic net. Type 1 error 0.11, type 2 error 0.04. Okay, slightly worse or better. So you see, elastic net has also these two, but the scale is different. So if you want to really compare them, we should have them in the same scale. And then we do the same thing for ridge. 0.19, 0.02. So you see, Ridge has the smallest type 2 error, largest type 1 error. So there's a trade-off here between type 1 and type 2. And then here we see that all of them more or less have the same pattern. A lasso and elastic net clamp the non zero. So we see that all three give more or less the same pattern, but it's hard to see here. But let's just look at them, at the numbers. So you see there are a lot of small numbers, but they are not exactly zero. But when we look at lasso, they are exactly zero. So they are just clamped to zero. Coefficients that are not significantly associated with the response are clamped to zero. That's it. All right. So now we create a data frame involving the feature matrix and the responses. We turn the responses into factors, and this part of the code concerns support vector machines, which we have not covered yet. That comes in the next lecture, but I will just go over the code because we will discuss about the meaning of it next week, but I want to get to the random forest after this. So let's just, I will just skip this for now. Let's just skip this. We don't need this. I will just run it. It takes some time. So support vector machine takes a lot of time. It requires a lot of cross-validation, but it's able to capture non-linear boundaries. And you see it has a small type 1 error and type 2 error because it's more flexible. But, well, let's just go for trees because support vector machines is subject of the next class. So trees, we have our data, we have this function tree, we have this vector y, which is a vector of our labels, and dat is a data frame. We give it to a tree, and if a tree is fit, then we use the predict function, give it data, and we get the predictions. Y hat, we have to take the second column. Well, let's just look at this first. Tree fit. So here is one way of expressing it, but we can also plot it. This is how our tree looks, and you can also add the labels. But once we get the y hat, this y hat has, so for each of these colleges, we have the probability that it is private, right? So the probability that it's 1 is 0.4545, the probability that 0 is 5454. So we look at the second column because we want the probability that it's 1, and we threshold it at 0.5, and then we calculate the false positive, true positive, total negative, type 1, type 2, and then we give the results. Now, this is a tree that is deeply grown. It is not pruned, and it is most likely overfitting the data, right? And in order to avoid overfitting, we want to prune this tree using cost complexity pruning. And the way to do it in R is to call this function CV3. We give it the tree and we just say prune based on misclassification. Well, it doesn't have to be misclassification actually. Let's look at this function for a second. So it runs k-fold cross-validation. The object of class tree. Fun is the function to do the pruning. And so we use the argument prune misclassification in order to indicate that we want the classification error to guide the cross-validation and pruning process rather than the default for the CV3 function, which is deviance. So let's just use the default because as we discussed in the previous ones, the deviance, which is the cross entropy, is more sensitive in the sense I described in the previous video lectures. So let's just remove this. So we have the optimum tree, and then this optimum tree has a size, has a deviance for the different sizes, and then we can pick the one okay, so we only care about the deviance. We look at the tree with the smallest deviance, and that gives us the specific size. And then once we have the size, we say, okay, prune based on this size. Okay, so let's stick to the misclassification because I don't know, apparently R isn't, or I don't know how to do it in R to stick to the deviance, because apparently what it calls deviance is also not really deviance. It's the number of cross-validation errors. So just to be, just so that everything we do is consistent, when we start with misclassification, then we should stick to it when we also want to prune using misclassification. Okay. So we prune it using the size, we find the optimum tree, we use predict, we threshold it at 0.5, false positive the rest, and it's very similar to the previous codes we had. And we see that the prune tree has a slightly higher train type 1 and type 2 error. Well, yes, because it is trying to avoid overfitting, therefore it may look that it fits the data less well, but in fact it is fitting the unseen data better. Okay, so trees actually we don't care that much. We care about random forests, because random forest is a combination of many trees, decorrelated trees. Decorrelated trees fit to bootstrap data sets, and we see how that will influence the performance of our predictions. Okay, so Y is the response, data is the data, mtry is the number of features we want to consider at each split. We set square root of p, then we use predict, and the rest is the same. And we see suddenly the train and the type 1 and type 2 errors are 0. Okay. So this is a pretty elaborate example involving lasso, ridge, elastic net, and random forest.